For chemistry, this is section 11-3, and there's quite a bit of calculating to do in this section, so you want to make sure you've got your calculator handy and probably some pencil and paper. All right. First of all, let's consider the equation that I've shown here. 2H2 plus O2 yields 2H2O. This tells us that 2 moles of hydrogen gas, molecular hydrogen gas, plus 1 mole of oxygen gas gives us 2 moles of water. Now, in actual fact, when you do this reaction, both the hydrogen and the oxygen at normal temperatures are gases, and the water that comes off of here is water vapor. In other words, it's steam, if you want to think of it that way, but it is not liquid water. Okay, and there's some interesting relationships that were discovered. First of all, we want to take a look at Gay-Lussac's law. Gay-Lussac's law says that at constant temperature and pressure, the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. And so this simply says that you never get like 1.7 moles of this one to 3.2 moles of this one. It's always going to be small whole numbers. 1 mole to 3 moles, 1 mole to 2 moles, 1 mole to 1 mole. Avogadro came along a while later, and he was right towards the beginning of the 1800s. And he said, he discovered the law that's now known by his name, Avogadro's law, and that says that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So what that tells us is that 2 volumes of hydrogen plus 1 volume of oxygen yields 2 volumes of H2O. So the number of molecules in the 2 volumes of H2O, if it's at the same temperature and pressure, would be the same as the number of molecules of H2O on the right-hand side. At any rate, these were very important properties in our discovery of, or in our work with gaseous products and reactants, which is what we're looking at here right now. What this leads us to is what is known as the molar volume of a gas. And what that says is that 1 mole of a gas at STP. Now remember, that's not something you put in your car. That stands for standard temperature and pressure. So 1 mole of a gas at STP has a volume of 22.4 liters. And so we refer to that as the molar volume of a gas. That number, and you should commit this one to memory, 22.4 liters per mole. This is the molar volume of a gas. Now this is kind of interesting because it allows us to solve some problems and make some predictions about gases that are fairly important. For example, let's take a look at a sample problem where we calculate the density of a gas. If you remember from way back in chapter 2, I think it was, we defined density as mass over volume, or we usually write that as D equals M over V. And so we know the mass of 1 mole of carbon dioxide, and that is 44.8 .0095. Now that's grams per mole. And if we divide that by the volume, which is 22.4 liters per mole, our moles are going to cancel out here, and we get 1.96 grams per liter for the density of carbon dioxide. Now, again, this is at STP. If you have other conditions present, that number would change. But the density of carbon dioxide. So we can calculate the density of any gas at STP, or we can do it under other conditions also. It just involves a little bit more calculating, as we'll learn here later on. All right, now we can also apply Gay-Lussac's and Avogadro's laws to stoichiometry problems, and actually do problems involving stoichiometry with gases. And this actually gives us another method, or another, if you will, set of possible problems. We can now add volumes of gases to the stoichiometry, and so we can now do mass volume, volume mass, volume volume, volume mole problems. So you have all those new combinations. Remember, before we had 4 between mass and moles. Now we add volume to that, and so there are I think 8 different possible combinations. However, let's take a look at a density, or a gas stoichiometry problem. Okay, so we look at this problem. It says assume that 5.60 liters of hydrogen at STP reacts with excess carbon or copper oxide according to the following equation. And you're given the equation there. It says balance the equation and then determine the number of grams of copper that is produced. So we're starting here with the number of liters of hydrogen gas, and we're being asked to find the number of grams of copper. Alright, so what we're going to do first, and this is the key to using this table. Now what you see, we've put in the volume line up above here. When you use volume, you go directly from volume to moles. Okay, so we're going to skip over the mass. We're going to use the number 22.4 anytime you do this. You can also go from moles to volume, again, by using the number 22.4, and it's the same rule that we had before. Divide down, multiply up. So we're going from 5.60 liters to the number of moles. We would simply divide that by 22.4. If we were calculating the volume, for example, in this we might want to know the volume of water vapor that's produced. We would calculate the number of moles here, and then go directly up here by multiplying the number of moles by 22.4. So this table works just the way as it did before, except you have to remember the 22.4 gets you from volume directly to moles. You take a direct route there. Alright, we were told to make sure that the equation is balanced, so let's do that first. We have 1 copper on this side, 1 copper on the right side, 1 oxygen on the left side, 1 oxygen on the right, 2 hydrogen on the left, and 2 hydrogen on the right. So that equation is balanced. Okay, and we could put our ratios in down here. Those are all ones. We also need the molar mass, or formula mass of copper, and that is 63.546 grams per mole. So now we can start doing our calculations. Again, remember the number that we want to remember is 22.4. It's actually liters per mole, and so if we in order to do this, we'll take 5.60 liters and divide by 22.4 liters per mole, and that ends up giving us 0.250 moles. That's the number that we would get right in here if we were interested in that. Divided by 1 times 1 still gives us 0.250 times the 63.546 gives us, to 3 sig figs, 15.9 grams. And so our answer to this problem then is 15.9 grams of copper. Okay, so you can see this table works very similar to how you were using it before. The only thing you have to remember is you go from volume to moles or moles to volume using the number 22.4. And again, the same rule: divide down, multiply up. All right, now we've looked at the combined gas law, which relates pressure, volume, and temperature. The one quantity that we saw way back in section 1 was that the number of particles, or the amount of moles of a gas, is also important. And so we're now going to take a look at how do you get that, how do you work that into the equation. And it's actually very simple. We have what's known as the ideal gas law. And the ideal gas law is PV equals nRT. Okay? Now, P, V, and T are pressure, volume, and temperature, just like you have seen them before. N, this number right here, is the number of moles of the gas. Okay, so N is the number of moles, R is the gas constant. And the value for R actually depends upon the units that are used for pressure, volume, and temperature, because they're all related. R is a constant that basically is going to cancel out. It has to have units that are equivalent to the other units that you have here. And so you have to choose the correct value for R based on the units involved in the problem. And I'll show you that here in the chart. Okay, now this chart is available more or less in your book on page 384. So I'll just refer you to that. But you can look here at this one. You'll see that the units of R, they look kind of daunting there. For example, the top one there is liter millimeters of mercury per mole Kelvin. These are the units that allow R to cancel out the other values that are used in that formula, so that our units remain consistent. Okay, but you can see that the main difference here in these is, for example, in the first one, the unit of pressure is in millimeters of mercury. In the second one, our unit of pressure is in atmospheres. And the third one, that you won't use real often, is in kilopascals. But those are the three common ones. There's another one given in your book. You're never going to see it. I'm not going to include it here. But you have to use the correct value of R for the units of pressure that are given to you. Otherwise, you're going to be doing it wrong, and actually you should find out that your units won't cancel. However, I know that most of you don't like to use units when you're solving a problem, and so you won't know that, and you'll just get the wrong answer, and you won't know why. But you'll see that as I solve a problem here, I will include these units, and that makes it possible for us to actually cancel and see what's going on. All right, well, let's take a look at a problem. Here we're given the problem: calculate the volume in liters of 2.00 moles of H2 at 22 degrees Celsius and 1.25 atmospheres. All right, so to work this problem, we'll start with writing out our ideal gas law. PV equals nRT. And then it's asking us to find the volume. So solve this for volume. So if we simply divide both sides by P, we get V equals nRT over P. So we have V equals, and we'll put our numbers in, N, the number of moles, that's 2.00 moles. R, the value of R, in order to know what is the correct value of R, we have to look up at our units of pressure. And our pressure here is given in atmospheres. So you can see we're going to use the unit, or the value 0.821. 0.0821, and I'm going to write those units in here. That's liter atmospheres per mole Kelvin. And then we have our temperature, which is 22 degrees Celsius. We have to add to that 273 kelvins to get our Kelvin temperature, and that is 295 kelvins. And then we're going to divide that by our pressure, which is 1.25 atmospheres. Okay, so when we do the arithmetic here, we find that the volume is equal to 38.8. What is the units? Well, moles cancel out moles, kelvins cancels out kelvins. We have atmospheres on the bottom, that'll cancel out atmospheres on the top, and we get our units in liters. And that's what we would expect, because that is a unit of volume. So we have 38.8 liters of H2 under those conditions. So you can see this is fairly straightforward. Again, I like to solve algebraically. If you don't like to do that, you want to just plug the numbers in there. Just be careful that you don't round until you're all done. Okay? All right, well, let's take a look at one other sample problem. Okay, this problem says a 1.45 mole sample of gas occupies 8.77 liters at 20.0 degrees Celsius. What is the pressure in millimeters of mercury? All right, now again, remember the correct choosing the correct value of R is important, and so let me show you. We're being asked to use pressure in units of millimeters of mercury. And so we're going to use this first value here, 62.4, and that is liter millimeters of mercury per mole Kelvin. So coming back down here, we'll start out by, well, first of all, let's change our temperature, because we're going to have to do that. 20.0 degrees Celsius is equal to 20.0 plus 273.15. Now, notice since we have a decimal portion here, I'm going to use this 273.15, and when I do that and I do the addition, let me show this to you in two steps. I come up with 293.15, but I have to round to the first decimal place there. Okay, and so I'm going to round this to 293 point. Now notice we have a 5 followed by nothing. So you have to use your rounding fives rule here. And the rule is to make it even. Okay, so we're going to round this to 293.2 kelvins. All right, then we'll start with our PV equals nRT. And we want to calculate P. And so we get P equals nRT over V. And again, we'll put our numbers in here. N is 1.45 moles. I'm going to write a little smaller here because I don't have as much space. R is 62.4, and this is liter millimeters of mercury per mole Kelvin, times our temperature, which is 293.2 kelvins, and we're going to divide that by the volume, which was 8.77 liters. Okay, so now again, if we look at what cancels out here, moles and moles will cancel out, kelvins and kelvins will cancel, and the liters down here cancels the liters on the top, and we get our answer in millimeters of mercury, which is what we wanted. Okay, doing the arithmetic then, and again to 3 sig figs, because we've got 3, 3, 4, and 3, so our answer should have 3. You come up with 3,020 millimeters of mercury. That's your answer for your pressure. Okay, so that is that's section 11.3.